Hey, good morning, everybody. So a couple of things. First of all, this is a help session. We're treating this as a help session, so make sure you see me before you leave. I don't mark anybody off for this, so just make sure that I get your name down before you go, just as you walk out. The exam is on Monday. It'll be in here. It'll be 20 questions with 8 multiple choice, just like you've seen before. Today I want to go over the free response. I made a little video for you. I don't know if you got that yesterday. To preview the free response for you, but I'll go over them in more detail today. And then we'll go over sort of the categories for the multiple choice. It is covered chapters 7 and 8. That's on, lenses and mirrors, and then on interference and diffraction gradients and single slit and double slit. So let's look at the free response. You're going to have 4 free response. The first one is going to be a 2-lens system. I'll ask you, what is Q2? And what is M total? What is the total magnification? And then what is the position of the final image? You're not going to have to deal with a virtual object. So it's going to be, you will not have to deal with a virtual object. So it'll be something like this. I'll give you 2 lenses. I'll give you the focal points, F1, F2. I'll give you an object. It'll be over here. I'll give you this distance. And then I'll ask you for those 2 things, Q2 and the total magnification. We can work through one of these later. There's a bunch in the free response, so just practice them. They're really just like two-piece lens questions. So the first thing that you do is you take P1 and then you calculate what Q1 is. If that object is going to be over here, you also calculate M1, which is negative Q1 over P1. And then you figure out what is P2. That's going to be this distance. I, of course, will give you the distance between the lenses. And then once you have P2, let's say that this is X. P2 would be equal to X minus Q2. The difference in the total distance minus Q1. Sorry, I said Q2, this should be Q1. And then I solve for whatever Q2 is. Q2 is going to be over here somewhere. I solve for Q2, solve for M2, which is negative Q2 over P2, and then the total magnification is equal to M1 and M2, the product of M1 and M2. And so what I'm looking for is this and this, but you have to go through all the steps to get to those, okay? No virtual objects. That means that your P2 will be positive because it's going to be to the left of the lens. The second question that I'll give you is a mirror question. There are 2 things that I'll ask you. I'll ask you, 1, what type of mirror, or A, what type of mirror is this? Is it convex, concave, or flat? It's not going to be flat. It'll be convex or concave. In order to answer that, you'll have to know your 4 different types of images that are produced by concave and convex mirrors. So for concave mirrors, well, for concave, if you have an image, there are really only 2. You can be outside the focal point or inside the focal point. That'll be my object. If I'm outside the focal point, the image is right there. The image is inverted and real. If I'm inside the focal point, my image is right here. This image is upright, virtual, and big. Okay? And then convex mirror, if my object is here, it's my object, my image is here. My image is upright, virtual, and small. So based on the way that I describe the image that's produced in this problem, you should be able to tell which of these is the correct mirror. I'll ask you explicitly, which mirror is this? You'll have to answer those questions in the multiple choice part too. By the way, some of the questions might help you in other questions, so be on the lookout for that, where information that I give you in one question, you can use in another question or to think about it. So if you feel like you're lost, don't get forewarned, just, look, sort of take a break and look at some of the other questions and see if they help you. So I ask you what type of mirror. And then I'll ask you B in this problem. What is it I asked you? I think I asked you, what is the image distance? Okay? But in the problem, all that you know is M. You would know the magnification, or at least you'd be able to calculate the magnification. But no secrets here. We've seen problems like this. I think that y'all, yes, you recognize what I'm talking about? We'll look at some in a multiple choice. You'll have your magnification, because I'll give you the dimensions of the object and the image, and so you can calculate the magnification. M is equal to the height of the image over the height of the object. And also, I'll describe it as virtual, bright, bigger, or whatever, and you'll be able to discern from these three scenarios what type of image it is. And then I'll also ask you, or no, I'll give you also the center of curvature. Okay? And remember that F is equal to C divided by 2. You'll need to make sure that the sign is right, because if I have one of these mirrors, they have a positive focal length. If I have the convex mirror, it has a negative focal length. So that will be very important that you get the sign correct. Once you get this, you can solve these two equations. Let's say the magnification is 2, for example, and the focal length, well, it would have to be positive 4. Say the focal length is positive 4 and the magnification is 2. Then I would say 2 is equal to negative Q divided by P. And then I would say 1 over 4 is equal to 1 over Q plus 1 over P. Okay? I have a system of two equations, and that's what you're going to have to solve on Monday, solving this system of two equations. It's a very useful skill to solve systems of two equations. If you're out and you're trying to impress somebody, I don't know, however you impress somebody, this is a good way to impress them, to say, hey, look, I can solve a system of two equations with two unknowns. And they'll say, wow, I want to get to know you more. So in order to solve this, what you do is you solve one side. Let's say, I would say Q is equal to negative 2P. And then I would take this and I would plug it in for Q over here. So I get 1 over 4 equals 1 over negative 2P plus, I'm going to go ahead and do 2 over 2P because that gives me a common denominator. And then I get 1 over 4 equals 1 over 2P. And then I'd solve that for P. 2P equals 4. No, that's right. And then P is equal to 2. So that's my object distance. If I wanted to know my image distance, I could take this and plug it into either one of those original equations and solve for my image distance. Okay, practice with that. You'll see them in the old test, in the homework, and in the back of the chapter. There are examples of this. Okay. Spring 19 had a free response, I think, that had a similar question. Okay, so that's one. Each of these has two questions, by the way. The third free response is a diffraction grading problem. Actually, I think this is the fourth one, but one of the four is a diffraction grading. I'll give you the spacing. So I'll say, for example, I have a diffraction grading with 1,000 lines per millimeter. One of the things you'll have to do is figure out what is the slit spacing. That's 1 over 1,000 in millimeters. Of course, you'll want to convert that into meters, so make sure you know your metric prefixes. By the way, these are the metric prefixes that you need to know, and you really need to know how to do these conversions just like that. You need to know milli is 10 to the minus 3, and you know centi is 10 to the minus 2, and you need to know nano is 10 to the minus 9. Pretty sure those are all the ones that you need to know, but I don't give them to you, and you do have to convert them, okay? For at least for the diffraction grading, single slit, double slit, all that needs to be in SI units. So I give you diffraction grading. I would tell you that the diffraction grading is a certain distance from the screen. Say, I don't know, L is equal to 5 meters or whatever. And I would give you the wavelength. Say the wavelength is 400 nanometers. And I would ask you, what's the distance between, say, the central bright fringe and the third order fringe, for example. To solve that, what I would be saying, I wouldn't give you this figure, but what I'd be looking for is what is the distance from here, that's the central bright fringe, to up here. What is y? There are two steps when you're solving this question. The first is to find theta. You say d sine theta equals m times lambda, and you solve that for theta. I know d, I know m is equal to 3 in this case, and I know lambda, all converted to proper SI units. So I solve for theta, and then I say y is equal to L tan theta. And that gives me the distance from the central bright fringe up to the third bright fringe. Be careful, I'm pretty sure that there's a question where I ask you not just that, but I ask you, oh gosh, what was it I asked? Oh, one question I asked, what is the width of the central bright fringe? And you understand that's a different type of question. Okay, actually, let's finish this. I'll come back to that. Okay, so that's not on the free response. But I could ask you for what is y. I might ask you what is the slit spacing, that is what is d. I could ask you for the angle somewhere along the way. I would ask you for some intermediate step along the way. Alrighty? And then number 4, actually this is number 3 on the exam, or maybe number 1, is I need you to draw a ray diagram. Mirror, lens, convex, concave. I'm only going to ask you to draw 2 rays though, so that makes it a little simpler that you can just pick out the really simple rays that you draw for, say, concave lenses, and just memorize those. Knowing the ray diagrams does help you. It helps you to remember what type of images, what type of lenses and mirrors produce, so I want you to know those. Ray diagram with 2 rays. For example, this is the simplest I would give you. I haven't done this question, so I don't know which one I'm going to give you. Sort of depends on my mood. Now, my tests never depend on my mood. The tests, you know that, right? Like if I'm angry, that doesn't mean that you get an angry exam. Or if I'm happy, that doesn't mean you get a happy exam. It's always the same. Okay, so let's say this is my convex lens. I would give you this. I would say, here's the object, draw 2 rays. You don't have to describe the rays. You don't have to tell me what the rays produce or anything. I just want you to draw the 2 rays. This one would have line go parallel to the axis and through the focal point. The other simpler one is to go through the focal point and then parallel to the axis. So those are the 2 rays. My image is right there. I might ask you to describe the image, actually. I'm not sure. Like I said, I haven't written this yet, so be able to describe it. For example, this is a real inverted image. In some cases, we know if the image is big or small, but we don't know that necessarily for this. Okay? So that's the free response. That's 8 questions. That's, what, a third? A little less than yeah, it's a lot of your exam. Okay? Let me talk about that. I brought it up. This isn't in the free response, but I just want to make sure that you're clear on how to do this, because I don't think that we've done an example explicitly in class, but you should have seen it as you've been practicing. If I have a diffraction pattern, whether it's single slit, double slit, diffraction grading, usually what we've been doing is we've been asking, what is the distance from here to here? And we've been calling that y. Right, we said that y is equal to L tan theta. But I can also ask, what is the distance from here to here? Okay? In order to do that, what you have to do is to figure out what is the distance from m equals 0 to up to this point. You would find, say, let's say this is for a double slit. You would find the angle theta. What is this angle theta? By saying d sine theta equals m plus 1/2 times lambda, where m here is equal to 0. Remember, d sine theta is your path length difference. And so your path length difference has to be a half a wavelength in order to get destructive interference. D sine theta equals half lambda. So I solve that for theta. Then the next step would be to find y. Y equals L tan theta. All right, find y. That's just like the other problems that we've been doing. But if I want to know the width of the central maximum, there's one additional step. The width of the central maximum, or the central bright spot, or the central fringe, is equal to 2 times y. Because this distance is y, and this distance is also y. They're symmetrical. So in order to get that total width of your central bright spot, you have to take twice that distance. Just be aware, there is a question on the test. I don't remember if it was single, double, or diffraction grading, but they all work similarly. Though with a single slit diffraction, you know, we're actually measuring the angle to the dark spots, not to the bright spots. Okay. So we can go through the exams. I sent you my mobile number, so I think it might be easier if y'all have explicit questions to send me a text. But listen, I'm going to show it on the screen because I forgot to bring my phone. I don't usually walk around my phone. I know y'all do, but I forgot to bring my phone. But I'm able to pull it up on the computer. So I'm about to pull up my text. So if anybody has sent me a text, everybody's about to see it. Okay? Y'all ready? Okay, good. Nobody sent me a text, but just beware. If you send me a text, everybody's going to see it. Okay? Are there any particular questions that y'all would like to look at? I'm going to scroll through some of the old exams. I'm just going to sort of leave this off to the side. So if you have a question, your name won't pop up unless you're in my contacts, which you shouldn't be. But anyway, let's look at some old exams. Let's go to the spring 19. I think that's exam 4, almost exclusively exam 4. And so exam 4 here, spring 19, it has the free response. Not all of my exams have free response. This one does. And good question here, number 1, you'll see a question like that. Number 3, yes, number 3 is like the type of image or type of question that you'll see. And then also the 2-lens system is very similar to what you'll see. So that's a good example of your free response, except it doesn't have the ray diagrams on it. That's something new. Practice this, try to do it on your own without using the solution and see how you do. If you do perfectly on this, you're probably good for the free response. In fact, if you do perfectly on this right now, you're probably pretty good for the whole exam. But let's look at some of these others, because some of the multiple choice can be complicated. Here's some things about the eye and spherical aberrations. You'll have a couple of questions. In fact, if I look at the categories of questions, this is how I categorize them. You just write this down for your reference. I say ray tracing mirrors. You'll have 2 questions about that. When I say ray tracing, I don't mean just that you have to trace the rays, because we actually have that in our free response, but what type of mirrors produce what type of images? Those sort of questions. And then ray tracing lenses, 2 questions as well. I might also ask you to identify lenses, what type of lens is this, those sort of things. These are more conceptual questions. Mirror equation. There are 2 questions on that. Lens equation, 2 questions on that. Eyes, cameras, and aberrations. We've had spherical aberrations and chromatic aberrations, and we talked about eyes and cameras and how they're different. 2 questions on that. No 2-lens systems in the multiple choice. And then in the next chapter, chapter 8, we have interference. Now you're going to see questions like, what is the phase difference for these two waves? Is it 0 degrees, 90 degrees, 180 degrees? Are they in phase, out of phase? Do they experience destructive, constructive interference? I might give you one of those questions where you have a funky waveform, and I ask you, okay, if I add these two waves together, what is the resultant wave? We've done one or two like that. So interference questions, you'll have two. Or maybe I have two waves that are traveling through space, and they travel these different distances. When they arrive at that point in space, do they have constructive or destructive interference, or something in between? So you'll see interference, double slit. You have 3 on this, because it's not in the free response. Double slit, I'll ask you what is the width of the central maximum, or what is the distance from the central maximum to some order. And then I'll also ask you some conceptual questions, like what happens if you change the distance between the slits, or you change the wavelength, those sorts of things. Double slit, single slit, similar. Although I think there are just 2 questions for that. And then diffraction gratings. Diffraction gratings, I could have several questions, but no, not 3, 2. So 20 total. So 2 questions for diffraction grading. 2, 4, 6, 8, 10. Oh, there are 3 interference. That's why. 3, right? Yeah. So for the diffraction gratings, I will give you what is the slit spacing, 1,000 ohms per millimeter, for example, and ask what is the distance between the slits. Or I'll ask you what is the angle to the first order diffraction, or the first order interference pattern, the fringe. Or I might ask you how many spots are there on the screen. And we did one like that where give you a diffraction grating and it produces a pattern like this. And remember, when theta exceeds 90 degrees, that means there are no more spots on the screen, that the diffraction pattern ends. It doesn't go on for infinity. And so you can do that by calculating what n is when theta equals 90, and then counting up the total number of spots. So 1, 2, 3, 4, 5. There will always be an odd number of spots because you have that central bright maximum that will make it an odd number. We did a problem like that last time in class that we were here. Okay? So of those categories, what do you want to look at? What is most pressing for you? You can text me or you can holler out, whatever you like. Yeah, Kenny? Interference? Sure. Okay. Y'all text me if you want. Maybe y'all have cell phones? My son, he has a phone, but he doesn't have actually coverage. Like, he doesn't have actually a signal, so it's really just sort of like, I don't know, a thing to listen to music. Does that y'all? You don't have cell phones. Okay. Interference. So interference. 2 things. We've done problems like this. Like, let's say that I have well, let's look in the old exam. I'll show you some examples of things. That's probably better. So, questions like number 17 and 18, where I ask you, what is the path length difference to create this interference pattern? But first of all, my waves have periods of 2, the waves have a wavelength of 2 meters, so the wavelength is 2 meters. And then second of all, I'm looking at a dark spot, so I know that the path length difference has to be some half wavelength increment. It has to be a half a wavelength, 1.5 wavelengths, 2.5 wavelengths, and on. I can count them up here. Here's the central maximum. So this is 1/2 wavelength, 1.5 wavelengths. This is 2.5 wavelengths. So my path length difference has to equal to 2.5 wavelengths. Since my wavelength is 2 meters, 2.5 times 2 is E, or 5 meters. You're going to have a question that's something like that. Look back at the old exams, there are variations on those, but you'll definitely have a question like that. Similarly, right here, number 18. by what amount are these two waves out of phase? Well, the two easy ones are these. This one is 0, right, because those are completely in phase. R360, so this is 0 R360. In fact, you could probably just get rid of A and E, because I'm not going to give you those two options for waves that are in phase. The other one that's easy to identify is one that looks like this, because these are 180 degrees out of phase. So I can get rid of D here because that's not happening. So that means that the answer is going to be C, 90 degrees. We never did 45 degrees. 45 degrees is just hard to draw. So that's a 90 degree shift. It also means that it has a half wavelength shift. Those are the types of questions that you'll see as regard to interference. Number 16, similar, is a good question for interference. Two waves travel through space. The first wave travels 7 meters, the second wave travels 10 meters. That means my path length difference is 3 meters. And when they meet, total destructive interference occurs. That means that the path length difference is some half wavelength increment. So the wavelength could be I don't think it's any of these, right? No, I'm sorry, it can't, yeah, I think he is the right answer. Let's double check, 16, let's see, 2 meters. Oh yeah, 2 meters, that's 1.5 wavelengths, right? Sorry, I can't think right now. Anyway. Huh? Right, 3 meters is 1 full wavelength plus a half a wavelength. Right, okay, thank you, Sam. Just had a brain fizzle. So that means that I travel 2 meters, that's 1 full wavelength, and then I travel an extra half wavelength, so it's 1.5 wavelengths if it's 2 meters. Okay? Be prepared for those. You'll see some similar ones for all of those. Okay, Tammy? Is that clear? Y'all clear? Courtney? Yeah, so my path length difference is 3 meters. I have these two waves that travel a difference of 3 meters. In order for me to have total destructive interference, the path length difference has to be some increment of a half a wavelength. The path length difference can be a half wavelength, it can be 1.5 wavelengths, it can be 2.5 wavelengths, and on and on. So if my wavelength is 2 meters, that would mean that the path length difference is 1 meter. The path length difference is 3 meters. The path length difference is, 5 meters. And on. These are the path length differences. Okay? So that's how we know that because my path length difference is 3 meters, and it gives me destructive interference, that's how I know that my wavelength is 2 meters. It's probably easier just to sort of go through and try each of those. Not really use a formula to figure it out, but just reason it out. What now? Sam? Oh, yeah. Yeah, let me repeat what you're saying, because not everybody hears you. That's clever. So she said, you take your path length difference and divide it by each of the options. So 3 divided by 3, oh, that's 1. That's not right. 3 divided by 17, well, that's not a half, so that can't be right. 3 divided by 2, oh, that's 1.5. So that must be the right answer. And then 3 divided by 1.5 is equal to 2. So that would actually give you a bright spot, not a dark spot. That's clever. I like that. That's good. That's a good way to think about it. Okay? Check my messages over here. No? Okay. Other topics that you want to look at in particular? These are the topics that we have on the exam. Yeah. Hold on, sorry. Let's continue looking at this 2019 exam. It's a good one to practice. I would, not that I'll use the questions on this exam, but it's really similar, because it has similar pre-response. So you might want to reserve the spring 19 exam until like, I don't know, Saturday afternoon when you're all ready, and then sit down just with that exam that you haven't looked at to see how you do on it. Okay, so single and double slit you said, right? Clear this. Okay, so single, double slit, and diffraction gradients all work very similarly. Let's try. Yeah. Sure. So first, number 13, if you have a diffraction gradient problem, this is going to be sort of one of your first steps. And as I said, this is going to be on your free response. So if I give you a diffraction gradient with 2,500 lines per millimeter, if I want to know what the slit separation is, I like to think of it as dimensional analysis. I have lines per millimeter, but I want to know millimeters per line. So I just take the inverse of it. I say B is 1 over 2,500. That's in millimeters. And then that's 0.04 times 10 minus 4 millimeters. But then I'll need to convert that into meters, 10 to the minus 7 meters. All right, so A is the right answer. If you have a diffraction gradient, that's going to be your very first step. All right, and then after that, it comes out to be very similar to double slit, which I don't see any good ones. So let's actually go on to another one. Well, let's do number 14 while we're here. So this diffraction gradient has a slit width D. So D is 1 times 10 to the minus 6 meters. Light wavelength is 500 times 10 to the minus 9 meters, nanometers. And I want to know how many bright spots. So I'm really looking for what is M. And when I'm looking for the number of bright spots, I'm always going to set theta equal to 90. So it's like D sine theta. That's 1 times 10 to the minus 6. But sine of 90 is just equal to 1. Is equal to M, that's what I'm looking for, times lambda, which is 500 times 10 to the minus 9. And then I solve this for M. This goes to 1. M is going to be 1 times 10 to the minus 6 divided by 500 that's equal to 2. Okay? If that's equal to 2, that means that my diffraction pattern looks like this. Because I got this second order on either side. So the number of spots would be 5. What if, for example, I find not M equal 2, but I find M equal 1.9? If I find 1.9, that means that I don't have this second order. So if that's what I had, then the answer would be 3. You'll see why that is, because I don't get that second order completely. It's like having 0.9 kids. You can't have 0.9 kids. 0.9 kids is no kid at all. Okay? All right. Let's look for a single slit. I don't see one on this exam, so let's go to another exam because they work a little bit differently. Oh, was there? Let's take a look then. Yeah, and you will have questions like number 19. While we're here, we'll go ahead and do this. Questions that ask if a single slit is used to create an interference pattern on a screen. If you increase the wavelength of the light, what happens to the width of the central bright fringe? On these, you want to look at the equation. So for a single slit, A sine theta equals m lambda. And I'm asking, if I increase the wavelength, if this goes up, I want to know what happens to this, because theta is directly related to the width of the fringe. If theta gets bigger, that means the fringe gets bigger. If theta gets smaller, that means the fringe gets smaller. So if lambda goes up, there's a direct relationship. Theta will also go up, and if theta goes up, it gets wider. But let's look at another exam to see if we can have a single slit to work through. Let's look at 2020. Okay, 25 is a good example. This is spring 2020. I think 25 is actually from here, one of the chapter problems in the back of your workbook. Green line of gaseous mercury at 546 nanometers, so lambda equals 546. Falls on a single slit apparatus. M is equal to 4, because it's the fourth dark fringe, and the angle theta is 0.092 degrees. I want to know what is the slit width. So this one's actually pretty straightforward. I say A sine theta equals m lambda. Here, remember that m refers to your dark fringes. So m is equal to 4 because it's a dark fringe. I'm looking for A, so that's going to be m lambda over sine theta. R4 times 546, which 10 minus 9, divided by sine of 0.092. And then whatever that answer is, it'll come out in meters, but then you'll need to convert it to millimeters. Okay, it's still not one that I like. Let's look for another one. What's our more difficult one? Oh, this is sound. Sorry we didn't get the sound. Sound a fun topic. I guess we could have crammed it in there, right? Could we cram sound in there? I guess we could have. Okay. And they don't always make it into the exam, but you will have a single slit problem for sure. Okay, number 16 is a good one. Let's look at this one. This is the spring 16 exam. Light of wavelength 610 nanometers is incident on a slit of width 0.2 millimeters, and the diffraction pattern is 1.5 meters from the slit. What is the distance of the second dark fringe from the center of the bright fringe? So what I have here is my diffraction pattern like this. I'm looking for the distance from here to here, so I'm looking for that distance y. This order number right here is m equal 2. This is m equal 1. Remember, a single slit, there is no 0th order. I count the dark spots. And so I do this similar to what I did before, where I do A sine theta equals m lambda. I have lambda here, I have A here, and I know the order number here, so I can solve this for theta. Okay? Then, after I solve that for theta, to find the distance, I say y equals L tan theta, where L is this 1.5. I'm not going to go through all those numbers because they're very similar to the problem that we did before. But they're different too, mainly that the order numbers refer to the dark spots, not the bright spots. Practice with that, practice, because when you get to single slit, you have to shift gears a little bit. Now, fortunately, the equation sheet has some clarity to it. Let me show you the equation sheet. Notice that this is for double slit right here. This is for single slit, and this is for diffraction grading. And this is just general, that we use that for all of them. But notice the double slit, I tell you bright or dark. For the single slit, I tell you dark. And then for the diffraction grading, we just deal with the bright spots. We don't deal with the dark spots. Okay? So keep that in mind. You will have that equation sheet on hand. Other questions? Yeah, is that Chloe right there? Spring 15 and 19? Okay. I got a note on my door yesterday from Delta Zeta. I was very pleased with. My wife got one too. Thank y'all. It made my day. It wasn't a very good day, but then it really did make my day. So I appreciate all my great folks in here. I appreciate all of y'all. All right, number 19. You said right, Chloe? Okay, Young's double slit apparatus is set up so that a screen is positioned 1.6 meters from the double slits and the spacing, What is the difference between the central and first bright fringes? Okay, so this is a good example of what you'll have in the free response. Still in the free response, it's going to be a diffraction grading. But after you find the slit spacing, the way that you work this is really similar. You'll probably have one in the multiple choices like this too. So it's good that you know how to do this. It's good that you asked about this. First, let's just write down everything that we know. This is a double slit. I know that the slit spacing, or excuse me, the distance to the screen is 1.6 meters. It might help you to draw a picture too. I want to know the distance from here, the central bright fringe, to the first bright fringe. So that's m equals 0 to m equal 1. I want to know that distance, which is going to be y. I know that the spacing between the slits is 0.04 millimeters. I'm going to go ahead and convert that into meters. And I know that the wavelength is 630 nanometers, or times 10 to the minus 9 meters. 2 steps in this. The first step is finding theta. And the same for your diffraction grading problem. It works almost identically, except you first find the slit spacing. So I say d sine theta equals m lambda. D is 0.04 times 10 to the minus 3. Sine theta equals 1. I use 1 because I'm looking for the distance from the 0th order to the first order. So I want to know what is this angle right here. There's my double slit here and here. I want to know that angle theta. And that's the angle theta to the first order fringe. Times lambda, which is 630 times 10 to the minus 9 meters. And then I solve that for the angle theta. I don't know what it is, I'm just going to leave it at that. But you find whatever the angle of theta is, it's usually pretty small. Then the next step is you say y equals L tan theta. Remember, on your equation sheet, that was that general equation at the end. It's really just the definition, your true definition for tan. Okay? So you say y equals L tan theta. L is 1.6 meters times the tangent of whatever your angle theta, so whatever theta is that you found here, you put in right there. And then that gives you your distance. Now I just want to double check that I don't need to double this or anything. It is true that I'm looking for the distance from here to here. So that is my answer, whatever that is. I don't know what the angle theta is, but whatever that is. Okay, Chloe, is that okay? All right. Yeah, Tammy? No, I say it because of this word. She said, how do I know I'm talking about the bright spots? Yeah, so I'm looking for the bright fringes. Now, the way that you know it's dark spots that you have to deal with is to say, what is the distance to the dark fringe? Or if I ask you, what is the width of the central bright maximum? I addressed that earlier. If you're looking for the width of the central bright maximum, which you are going to have to do on Monday, okay, you will have to find the width of the central bright maximum. In that case, whether it's single, double, slit, diffraction grading, what you do is you find this distance. So the first dark fringe, A sine theta equals m lambda for single slit, or D sine theta equals m plus 1/2 lambda for double slit or diffraction gradients. So I find that distance, y, and to find the total distance, that's just going to be 2y. And of course, y will be an option, right? So you got to double it in order to find the answer, which will also be the option, but that's the correct option. Okay? Other questions? You can raise your hand or you can text me. I feel very sad that y'all texted me, but nobody's texting me. Oh wait, oh look at that. Okay, double slit. Double slit. All right, let's do this number 16 on exam 2019, but then we'll come back to the double slit. Huh? Number 6. Okay, let's just recap that though. Oh wait, no. Number 16. Okay, number 16. Yeah, so remember Sam's tip on this, which is that you take your path length difference. Here my path length difference is equal to 10 minus 7, or 3 meters. And then I ask, well, I'm looking for destructive or constructive. I'm looking for destructive. That means I'm looking for something with a half in it. And then for each of these options, you divide 3, the path length difference, divided by the options for the wavelength. Here I get 3 divided by 3, that's equal to 1. That can't be the case because that would give you a bright spot. Here I get 3 divided by 17, but that's some decimal, that doesn't work. Here I get 3 divided by 2, that's equal to 1.5. So that's my answer because that path length difference is 1.5 wavelengths. 2 is the wavelength, 3 is the total distance covered, so 3 divided by 2 is 1.5 wavelengths. And then this would be 3 divided by 1.5, which is 2 wavelengths, which means that you would get a bright spot. Okay? All right, double slit diffraction. Well, double slit diffraction, there are a couple of different things we could look at. You know, how to solve those problems, which you just did one like that, I think, right? Or we could look at conceptual things with double slit. What do you want to do? Okay, these were from 20 minutes ago, so I think that we've done that. Okay? I think we're good on these. Let me know if that's not true. Yeah, Courtney? To find the central slit width, or the central width of the width of the central maximum? Yeah. Okay, yeah, sure. So when I have, let's say I have a single slit. Single slits like that. It produces a diffraction pattern that looks like this. Now if I want to know the angle to the first dark fringe, I can do this. I can say theta. And I can find that by saying A sine theta equals m lambda. I can solve for theta. If I know the slit width, if I know m, the order number, actually m would equal to 1 in this case, because I'm looking to that first order dark fringe. Then I can also find the distance to that, y, the distance y, by saying y equals L tan theta. But sometimes, if I find that distance y, if I look at my fringes, here's my bright spot. Oh, it looks dark, actually, it's doing yellow. Here's my bright spot, bright spot, bright spot. Just like we saw on the screen last time, when I had the laser shining on the screen. If I do that and find y, that's just this distance. But sometimes I want to know this distance. What is the width of that central bright spot? And to do that, I say twice y, because it's symmetrical. So if I find y, I just double it to find the width of the central bright maximum. Okay? I think that's all the time that we have for today. So make sure that you come by and see me before you leave. I haven't marked anybody down. And I'm going to post this, I think, the sound.